Okay, ladies and gentlemen, let's continue with convection heat transfer. Today we are busy with chapter 8 in the textbook of Cengel and Ghajar, the chapter on internal forced convection. Before that we did chapter 6, which is the fundamentals of convection, and also chapter 7, which is external forced convection. In internal forced convection, we've looked at firstly laminar flow and then turbulent flow. With the previous lecture was a very quick lecture with lots of equations. Does it make sense to go through all these equations one by one by one? All of them have in the Nusselt number, it's a function of the Reynolds number and the Prandtl number, and then there are a few who also take into consideration viscosity ratios. The equations as presented in the textbook are not all the equations that are available in literature. It is some of the most important and the most classical ones, from the first one to sort of the later ones of Glinsky and Petkov, and those are the equations that you have to select from when you do a problem where you have turbulent heat transfer. In laminar heat transfer, it is very important to know what happens on the wall. Is it a constant heat flux or is it a constant wall temperature? Depending on that, that will influence the Nusselt number, 4.3 for a constant heat flux, 3.6 for a constant wall temperature. But unfortunately, it is not that easy. That is only for the flow if it is fully developed. And in most cases, flow will not always be fully developed. There will be an inlet part, and that have to be taken into consideration. And that will always depend on the length of the tube that is being considered. Right. Now, since we've done all the equations, let's do an example so that you can get a better feeling of how do we use the equations which are available for turbulent flow. Okay, now the example that I'm going to do is a solar application example. You all know that in our country at the moment we have huge challenges with energy, and in most of our houses the heating of water is one of the most expensive items. Okay, and an alternative for that is obviously solar. Okay, so let's look at a solar application. Let's suppose that is the solar panel. Okay. And I'm going to do it very simplistic. Okay, and this is our storage tank. And this solar system works with a storage tank with a pump, and the inlet temperature is 10 degrees Celsius. Okay, and we pump the water through a tube, okay, which is in the solar panel and back. And we want an outlet temperature of 60 degrees Celsius. Okay, I've shown it as one cycle. Obviously, there are many different alternatives that you can do in the configuration, but just to keep things very simple. The mass flow rate is equal to 0.03 kilograms per second. Okay, and in this solar panel, what we will have is the following. That is the tube. Okay, so it is a circular tube, and the diameter of the tube is 15 millimeters, if I remember correctly. I will make sure a little bit later. So I think I've selected a 15 millimeter tube, and here we will have glass. Okay, there's the glass, and here we will have an aluminium foil typically. And the tubes will be black on the outside, so special paint will be painted over it. And the idea, of course, is that if this is the sun, okay, it all is rays, okay, that some of it must obviously go directly through the glass. Then we want to select a very special type of glass that once it is through, that it cannot actually go back. And there is glass like that. It is a very special type of glass, and that is actually be covered in one of the later chapters that you can, if you want to do the course in the second semester, we will give attention to that. So if it is reflected, then yes, some of it will go back, but most of it will also be reflected back, and the result would be that we will have this reflection all around the tube, so that for this case we have a constant heat flux of 200 watts per meter. Okay. So every 1 meter of tube, the solar radiation that we can capture would be 200 watts. Okay, and we are asked to determine the wall temperature of the tube at the outlet. Okay, the wall temperature of the tube at the outlet, the heat transfer rate, and then also the power required by the pump. Okay, how much power is required? How much kilowatts is required to pump the water through the solar system? Yeah. Are you all happy with the problem? Do you understand it? Okay. So, in terms of the water, we are going to need the properties of the water, and the bulk temperature is a good representative type of value that we can use. In this case, what bulk temperature are we going to use? Doesn't really make sense to use 60 because yes, the water at the outlet is going to be 60. Doesn't make sense to use 10 because it starts at 10, but it also doesn't make sense to use 100 or 200, isn't it? So the average would be a good value, which is in this case 10 plus 60 divided by 2, and that would be 35 degrees Celsius. Okay, that's the bulk temperature. So at this bulk temperature, we can now go to our tables and get the properties of water. The density would be almost 1,000 or 994 kilograms per cubic meters. The CP value is equal to 4183 joules per kilogram Kelvin. The viscosity is equal to 7.196 multiplied by 10 to the minus 4 kilograms meters per second, and the Prandtl number at that average temperature would be equal to 4.929. Oh, and the thermal conductivity of the fluid, of the water, would be equal to 0.610 watts per meter Kelvin. Okay? So, obviously, and the other question that we need to know is what must the length be of the tube through the solar panel? I forgot that. Okay? What should the length of the tube be through the solar panel? Okay. Are you all happy? Are you all with me? Any questions? Nothing. All right. So, in many cases, when we get a problem like this, be careful that you do not immediately start calculating heat transfer coefficients and everything that you can. Because sometimes the answer is just before you, and in this case, it is one of those cases where if we want to calculate the heat transfer rate, we actually have everything. So the heat transfer rate is equal to the mass flow rate, the CP, multiplied by the outlet temperature of the water, minus the inlet temperature. The heat transfer rate to the water would be equal to the mass flow rate multiplied by Cp multiplied by the delta T. In this case, that would be TO, the outlet temperature, and that would be TI, the inlet temperature. Right, let's do it. The mass flow rate is given as 0.03. The Cp is equal to 4183. And the temperature difference we want is 50 degrees Celsius, or 60 minus 10. Okay. And the result would be 6,274 watts, or about 6.3 kilowatts. 6.3 kilowatts of heating of the solar system. Right, now, this is how much we need. We need 6.3 kilowatts. For every 1 meter, we can get 200 watts. So it is very easy to determine the length required. So we can say that the heat transfer rate would be equal to that heat flux multiplied by the length. Okay. And this is equal to 6,274. For every meter of length, we can get 200 watts from the sun, multiplied by L, and the result would be 31.37 meters of tube being needed to do that heating. Does it make sense? Right. So, in this system, if we now look at the temperature as a function of x, then at a length of 31.37 meters, okay, at that length, the temperature will be 60 degrees Celsius. Okay. And the inlet temperature was 10 degrees Celsius. And in this problem, for every meter, we put in 200 watts. So the temperature rise would obviously be linear. Okay, we can derive it. We've done it previously, but it is so logical, we're not even going to do it, isn't it? Okay, so from 10 to 60, the water temperature is going to do that. And that temperature there is the bulk temperature, which is 35 degrees Celsius. Okay? Right. Now we have to go and get the surface temperature. Therefore, we need the heat transfer coefficient. To get the heat transfer coefficient, always the first thing we have to make a choice between is the flow laminar or turbulent? So the obvious thing to firstly do is to go and calculate the Reynolds number so that we know in which range we is. Okay. Now, for the Reynolds number, we need the velocity. We can get it from the mass flow rate is equal to rho multiplied by the area multiplied by the volume. Okay, the density is 994. Okay, multiplied by the cross-sectional area of the tube, pi divided by 4, multiplied by the diameter, which is 15 millimeters, square multiplied by the velocity v. Okay, multiplied by the velocity v. And from this, we can solve the velocity as 0.1708 meters per second. Continue here. Now we can calculate the Reynolds number. The Reynolds number is rho Vd divided by the viscosity. The density is equal to 994 multiplied by the velocity. We've just calculated it as 0.1708. Multiplied by the tube diameter. It's a round circular tube, so we do not have to calculate the hydraulic diameter or anything like that. So it is equal to 0.05 divided by the viscosity, which is equal to 7.196 multiplied by 10 to the minus 4. And the result is a Reynolds number of 3,539. And we looking at that, it's obvious the flow should be turbulent because the critical Reynolds number, where the flow changes from laminar to turbulent, is at a Reynolds number of 2,300. Okay, and that is larger than 2,300. Okay, you all happy with that? Any questions? Anything that you do not understand? Anything you're not sure about? Right. Now, that was the long way of calculating the Reynolds number. I hope you will remember that at a stage when we went through the theory, I've also pointed out that it is actually very easy to, in the Reynolds number equation, okay, look at the fact that we have the velocity multiplied by the density, okay, that to there, okay. And obviously that area can be written as a function of diameter, so it is very simple to derive that the Reynolds number can also be written as 4 times the mass flow rate, pi multiplied by the diameter divided by the viscosity. So it is just a quicker way of calculating the Reynolds number if the mass flow rate is given. Okay. Right, now that we know the flow is turbulent, we can go and look at our textbooks and we can look at all the equations in the textbook for turbulent flow. If you have your textbook here, you can please take a look at it, or I've summarized some of the most important ones here, but without the writing in between. So if we just quickly look at those equations, there's one, the first one is calculating the friction factor for that equation there. Then we've got that equation, right? Then we've got this one, which is called the Dittes-Boelter, which is one of my favorites. And the reason for that is because it is the simplest almost of all of them. Okay. So if you quickly want to do a calculation, you can get it, or if you've used a complex method of calculating the Nusselt number, you can very quickly check it with this calculation and at least see if you're not out with an order of magnitude. And there goes all the equations. Right. So what we're going to do now is let's use the most complicated of all and the one which is claimed to be the most accurate, and that is the Gliński equation, equation 871. Okay, so Gliński equation 871 in your textbook of Cengel and Ghajar. Okay. And even before we do it, before we do it, what you will see in the equation is a F. So we first need the friction factor in any case. So let's first use the Petikov equation. That is that first one for the friction factor. And that equation says the friction factor is equal to 0.790 multiplied by the lim of the Reynolds number minus 1.74 to the minus 2. Okay. This is one of many equations. Okay, there are more accurate ones, some that you have to solve iteratively, some that you can solve directly. Okay. But I'm going to use this very simple one, and if we do that, then it is equal to 0.790 multiplied by the Reynolds number, the lim of the Reynolds number, 3,539 minus 1.64 to the minus 2, and the result is a friction factor of 0.04312. Friction factor of 0.04312. Okay. Are you happy with that? Okay. As a responsible engineer, the first thing I would do is I would frown about it. And the reason for that is it is very simple to make a mistake, and it is so simple to just go and look on your Moody chart. So the responsible thing to do is to go and look on your Moody chart where you've got the friction factor as a function of Reynolds number, and that Moody chart is on page 891 in your textbook, one of the appendices, page 891, and we've got the line for laminar flow, which is the friction factor divided by 64. 64 divided by the Reynolds number for laminar flow up to about 2100 to 2300. Then we've got the transition region, okay, and then after that we have all the different lines, and this one is for the smooth tube. Okay, so at that Reynolds number of 3500, you can go and check if the friction factor is equal to 0.04312. You will not be able to check if it is 0.043. You will get to 0.04, but after that it would be very difficult. It is a logarithmic scale, so it is not so easy. But one thing that you must see that I've done is I've used a smooth tube. Okay, why did I use a smooth tube? Well, firstly, they didn't give me more information, and the second thing is almost all the tubes that you can buy these days, all the hard-drawn tubes, the soft-drawn tubes, if you look and go and measure the surface roughness divided by the diameter, I assure you for all practical purposes, they are all smooth tubes. With time, you will get corrosion or erosion, or in this case, scale on the inside. Okay. That would obviously cause the friction factor to increase, okay, then it will cause the equation, the Nusselt number equation, to be higher, okay. But that wouldn't be bad for us because we want actually a conservative value for the heat transfer coefficient in any case. Okay. So now that we've got the friction factor, let's use the Glinsky equation. And the Glinsky equation says the Nusselt number is equal to the friction factor divided by 8 multiplied by Reynolds minus 1000 multiplied by Prandtl, everything divided by 1 plus 12.7 multiplied by F divided by 8 to the 0.5, Prandtl to the 2/3 minus 1. Okay. Something like that. You can go and check. Equation 871. And I believe it's up there on the screen also. Aaron, if you can just go up quickly there to the equation. Nusselt number is equal to F divided by 8 multiplied by Reynolds minus 1000 multiplied by Prandtl, and then divided by 1 plus 12.7 multiplied by F divided by 8 to the 0.5 multiplied by Prandtl to the 2/3 minus 1. The range is the Reynolds number larger than 3000, so we've just made it. So we are in a range, and the Prandtl numbers must be between 0.5 and 2000, and our Prandtl number is 4.9, about 5, so we are in a range and we can use that equation. Okay. Okay, now forgive me, I'm not going to put in all the values. I'm sure you can do that yourself. It is very, very simple. We've got the friction factor, we have the Reynolds number, we have the Prandtl number. You just need to go through the motions and calculate the Nusselt number, and the result is equal to 24.37. Nusselt number of 24.37. Okay. Right. From the Nusselt number, we can get the heat transfer coefficient. The Nusselt number is equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity. The Nusselt number 24.37 is equal to the heat transfer coefficient multiplied by the diameter, which is 15 millimeters, 0.05, divided by the thermal conductivity of the water, 0.610, and the result is a heat transfer coefficient of 992 watts per square meter degree Celsius. Okay. Now, in principle, what does the heat transfer coefficient mean? It means that if you've got a wall, okay, there's the wall, and here's the bulk temperature, then it would give the heat transfer rate. Q is equal to the heat transfer rate multiplied by the area multiplied by the temperature difference. Okay, that is the meaning of that. So, in this case, we do have the heat transfer rate. So the heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area. Now, what temperature do we use? What temperature do we use? Okay. Well, what I'm going to do is I'm going to use the bulk temperature. Okay, so I'm going to use that one, and I'm going to explain to you just now why, and you're going to see it is very simple. So what I'm going to do is I'm going to say, let's use the bulk temperature, the wall temperature minus the bulk temperature, because the wall must be at a higher temperature than the water, otherwise there can't be heat transfer. You agree? Okay. Okay. So the heat transfer rate is equal to 6274, equal to the heat transfer coefficient, which is 992, multiplied by the surface area for heat transfer, and that would be the total length of 31 meters multiplied by the outside surface. So it is equal to pi multiplied by 0.05 multiplied by 31.37. Okay? And TW minus T bulk. So I'm just going to solve it as the temperature difference. Okay? You all happy with that? Okay. So if we solve it, then that temperature difference must be equal to 4.278 degrees Celsius. 4.278. Okay. Right, let's go back to the sketch. Okay. Let's go back to the sketch. So the temperature difference, temperature of the surface minus that, should be equal to 4.2. So there's the wall temperature. Okay? So it is equal to 35 plus 4, so that temperature would be equal to 39.278. Okay. That would be the delta T. If I would now use that one, then I can get that temperature there. So if the bulk temperature, T bulk is equal to 35, we can solve the wall temperature as 39.278 degrees Celsius. Okay. Do you agree with me? Okay. Now, they asked actually to calculate the wall temperature at the outlet. Okay. So if we do the same calculation for the outlet, okay, so if we say 6274 is equal to 992 multiplied by the surface, 31.37. Now the wall temperature at the outlet minus the bulk temperature at that point. Okay, remember, that is the heat transfer rate, that would be the bulk temperature at that point, and that is the outlet temperature of the water, it is 60. Okay, so the wall outlet temperature would be equal to 64.278 degrees Celsius. Okay. Right. And we can go, and if you do that, then it means that that delta T is actually exactly the same. So if you look at that delta T, it would be exactly the same, and the result is that the wall temperature is also a linear line. Okay? We know that if the flow is turbulent, then it is 10 diameters before the flow is fully developed. Okay. Now 10 diameters would be, for this problem, 150 millimeters. 150 millimeters, only 150 of 31. Okay. So in this region, the heat transfer coefficient would actually be a little bit higher. Okay, and therefore the wall temperature would actually be a little bit lower there. Okay, but globally, with this problem, what we will say is, we forget about that, it is not so important. The delta T right through is equal to 4.278 degrees Celsius. That is typically what will happen with the wall temperature as the water flows through it and as we get heating. So this temperature here of the wall would be equal to 64.278 degrees Celsius. Okay? Make sense? You don't look sure?
I actually want to find out what influence will bend on the
yes.
and on the Reynolds number and the power needed by the pump. And if it is bent, how is it actually measured? Is it the
It is a very good question. So the question is, what about the bends? Okay. Now in the bends, there are two things that will happen. If we look at this bend like that, okay, what we will have is we will have again secondary flow because of the centrifugal forces. The result of that would be that the heat transfer coefficient is higher there. Okay, every time you go through the bend. So if you do all the calculations again, like we've done, you are conservative. Okay. So it will actually just mean that the wall temperatures every time you go through a bend would actually go a little bit down. Okay. But this would be the average of everything. Okay. So that's the first part of the question. The second part is, yes, obviously the bends would increase the pressure drop, and that is part of the calculations that we're going to do now. Not the bends itself, but only the total length, and I will make a comment at the end. Okay. Any more questions on the heat transfer part? Nothing? Okay, so let's get to the pump power required. The pump power required from the pump is equal to the mass flow rate divided by the density multiplied by delta P. Okay, or is equal to the volume flow rate multiplied by delta P, whichever equation you want to use. Okay, so we must first get the pressure drop. Okay. The pressure drop we can get from delta P is equal to F multiplied by L divided by D, rho V square divided by 2. Okay. Friction factor multiplied by the length divided by the diameter, rho V square divided by 2. The friction factor we have solved as equal to 0.04312 multiplied by the length, which is 31.37, divided by the diameter, which is equal to 0.05. The density is 994. The velocity is equal to 0.1708 square divided by 2, and the result is a pressure drop of 1,307 pascals or 1.3 kilopascals. Pressure drop, 1.3 kilopascal. Okay. So now we can calculate the pump power. It's equal to the mass flow rate divided by the density multiplied by delta P. Okay, I'm not going to put in all the values, but the result is 0.0394 watts or 39.4 milliwatts. When I've done this calculation, I thought that I've made a mistake. I did go and check it. You can go and check it again. Okay? But coming back to your question is that, remember, this would be only for a length of tube of 31 meters. Okay. 31.37 meters. Okay, that would that pressure drop be. So it doesn't take into consideration the inlet effects, the outlet effects, the bends, okay, and maybe the effect that you have to pump it up higher, okay, and down, which should cancel, okay. But because the power requirement in any case is so small, in many cases, if you design it correctly, you actually do not need the pump, okay. Just by the temperature differences, this thing will circulate itself if it is correctly designed, and you can get away without the pump. Okay? Any questions? Nothing? Okay. Now, let's suppose, I just want to show you a few more things. Let's look at the case of the lazy person like me, okay, which would have said that, this is a lot of work using the Glinsky equation. I'm going to use something else. I'm going to use the Dieters-Boelter. The Dieters-Boelter. And let's look at the Dieters-Boelter again quickly, Aaron. There it is. It's equal to 0.023 Reynolds to the 0.8 Prandtl to the N. So that would, the Nusselt number is equal to 0.023 Reynolds to the 0.8 Prandtl to the, and in this case 0.4 because we do heating. 0.4 for heating, 0.3 for cooling. Okay. And the result, if you calculate the Nusselt number, is equal to 30.05. Okay. 30.05. If we compare it to previously 24.37. So we can see a significant difference. Okay. But if you've done that, calculated with the Glinsky, and you do that quickly, you will feel quite comfortable that most probably you didn't make a big mistake and you do not have an order of magnitude error somewhere, which is always very helpful. Okay? Right, now if you go through all the calculations that we've done, calculate the heat transfer coefficient, then you calculate that the temperature difference, the wall temperature minus bulk, which would be 3.5 degrees Celsius. So in this case, using the Dieters-Boelter, the wall temperature, let's look at this case again, this one here, the wall temperature now would be 3.5 degrees higher, so it would be 63.5, according to the Dieters-Boelter. Okay. Another one, which is a headache for many students, is the one with the viscosities, okay, which is the Sider and Tate equation. Sider and Tate. Okay. Now with the Sider and Tate equation, I need some more space. Clean here. Okay, now the Cedar and Tate equation, let's look at that one quickly, Aaron. That one there, equation 869. Okay, Cedar and Tate, equation 869. Okay, and this equation says the Nusselt number is equal to 0.027 multiplied by Reynolds to the 0.8, Prandtl to the third, and now it has this ratio of the bulk viscosity divided by the wall viscosity to the 0.14. Okay. Now the bulk viscosity would be at 35 degrees Celsius. Okay, because we've chosen the bulk temperature as the average between inlet and outlet, and that is the value that we do have at the moment, which is 7.196 multiplied by 10 to the minus 4 kilograms per meter second. Okay. Now the problem is, what is the viscosity on the wall? If you've done this, then you know, typically, it's about 3 to 4 degrees higher. But if you haven't done it, you do not know. So you have to either guess 5 degrees, 10 degrees higher. So you can go and select maybe 45. You can get the value, okay? Put it in there, go through the calculation, calculate the wall temperature, see what it is, and then adjust the wall temperature calculation. Okay. So you will see that this one takes more time, but it is important because this is the thing that you have to check out for. So if you now, after you've converged with this problem, and you get the wall temperature, or you go and calculate the viscosity at the wall temperature of 39.2, which is equal to 6.622 multiplied by 10 to the minus 4 kilograms meters per second. So you can start with it at 45, calculate the Nusselt number, calculate the heat transfer coefficient, calculate the wall temperature. See that you've selected too high, go through it again, and then very quickly it will converge to that wall temperature. But the thing that you can check for is the following, and that is that the bulk viscosity divided by the wall to the 0.14. Okay, for this case is equal to 1.012. Okay. What does it mean? It means that for this specific problem that we are doing here, the viscosity effects are not important. Therefore, it is not an appropriate equation to use. You don't know it before the time, you know it after the time. However, things like water, typically 10 degrees, 20 degrees delta T, normally never an issue, but oils, mercury, and other stuff, then there will be very, very large ratios. But in any case, if you go through it, then you will calculate that the Nusselt number is now 32.09. Okay, 32.09. And the difference between the wall and the bulk is 3.2 degrees Celsius, which is actually not bad. Okay, so it is not a bad equation in any case to use. It will give you reasonable answers. If you look at Glinsky, the most accurate 4.2, Dittus and Bulter 3.5 to 3.2. It is not that it is 30 degrees or 40 degrees or 100 degrees delta T. It is sort of all the same answer. Any questions, ladies and gentlemen? If not, thank you very much.